Hello, my name is Ryan Holzman, and today I will be presenting an example and explanation of LU decomposition for INSOL's 2014 Spring Linear Algebra class. Now, a couple of things that LU decomposition is used for is, of course, solving basic systems of equations. It uses Gaussian elimination. This is a special algorithm designed that is recursive to put matrices into their near reduced row echelon form. It's more efficient for computers to solve with this, as it is a recursive function and is something that we can code, maintain, and test. It's also faster when a matrix is a square, meaning that its rows and columns amount is equal. You also can find the inverse of the matrix by using LU decomposition. This is one benefit. It does determine the inverse matrix when you use Gaussian elimination at the same time with no extra processing time, and if done correctly, no extra memory usage also. A of x equal to LU of x equal to b basically states that A is equal to L of U. B, being the identity matrix, means that some matrix X exists such that it is an inverse matrix that when multiplied by A will produce B. And lastly, we can use it to compute the determinant. So to start off, we should define LU decomposition. We can decompose A, the matrix we are given, into an upper and lower matrix. The upper matrix will be solved for a near reduced row echelon form, and the lower matrix will store the values of the coefficients we've used to do that. The steps to solving with LU decomposition are: initially you want to set up your equation so that your initial matrix A is multiplied by an unknown matrix X and is equal to the identity matrix B. As we know, A can be broken down into the L and U lower and upper matrices, and I will show you how to do that in just a second. And we know that A times X is equal to some identity matrix B, but that also means that LUX is equal to B. So we should consider these things: that there is some matrix D that when the upper boundary is multiplied by, the upper matrix is multiplied by some matrix X that will give us D, and then we can multiply the lower matrix by D to find B. The first step you would do is you would use the matrix you found in near reduced row echelon form, which is matrix L, have some unknown matrix B, D. B is the identity matrix, and so you will set L times D equal to B. After solving for B, we can use back substitution when we have the upper matrix U times some matrix X is equal to D, and we can solve for X, which will be our inverse matrix. This is the first step in how you would break down matrix A into the basic definition of the lower and upper matrices. The lower matrix will have a diagonal of all ones with L21, L31, and L32 storing the values that we use as coefficients to solve for the matrix U, which is the near reduced row echelon form matrix. The matrix inverse, A, or the inverse of matrix A, is matrix X. And when those two are multiplied together, you should receive the identity matrix B, which is your standard diagonal matrix, or matrix with a diagonal of ones and all zeros in all other spots. One of the key pieces is we can take A times X and do each row independently for our inverse matrix. So to receive the first column of values for our inverse matrix, we would multiply A times the first column of X values we would like to find and solve it just for the first column of the identity matrix. We can do this for each column of the identity matrix and therefore find each column of the inverse matrix. Oh, sorry, one too far. So the first example I'm going to cover was not actually located in the book. LU decomposition is something that we as a group were in the group for our final presentation found while researching different Gaussian elimination things that could be coded that are recursive. LU decomposition goes one step further than just your basic Gaussian elimination and also provides you with a matrix inverse at the same time. So here we're given a system of three equations and their values and their corresponding answers. I went ahead and converted them into a matrix. It is not an augmented matrix though, as you can see here. The first step is Gaussian elimination. So we'll start with our base matrix here. How we start that is, we have to come up with the coefficients that we will use for that. The way that is done is, first we will skip the first row, as it is already appropriately formatted for reduced row echelon form. When we get to row 2, -3 should be used as the numerator, since that is what we were trying to get to 0. We will then use the top left value of 10. Since we are solving the first column to get all zeros in the lower values, we will use the first row and the first column's number for the denominator for all values we do this for. As you can see, to take care of the second row, we will use a coefficient of -3 over 10, and for the third row of 1 over 10. By multiplying the corresponding rows by that, we were able to come to this matrix here. One of the key things you will see as a difference here is we went ahead and stored the values we're using for coefficients in the matrix versus just putting zeros there. That is one way when coding this to work with computers that we can minimize memory usage. The -0.3 is stored there versus a 0. Of course, we know anything in the lower matrix should be 0. We are able to take, and instead of just storing a 0 there and having a second matrix E, we are able to store the values there. So we will go ahead and move on to the next portion of the matrix. What we will be solving for here is row 2, row 3, column 2. What we will again do is we will be using what we were trying to solve for as the numerator, and then we'll be using the value above it as the denominator. We're solving for the second column, so we will use the second row, second column value for the denominator for all of these operations. Here we can see that we will multiply this row with the coefficient of 0.8 over -5.4. This will become a 0 value here, but we are again storing the coefficient we've used for that there, and we would have a value for our diagonals of 10, -5.4, and 5.352. When we actually split this matrix into the L and U pieces, in the next step, you can clearly see that we have all zeros here as where needed for reduced row echelon form, and we also have our coefficients stored in those of corresponding values here. This is just a trick to help minimize memory usage. You would actually leave these two as a single matrix inside of a computer program if you were doing this in that way. For LU decomposition, when you're doing it by hand, it can be easier to go ahead and store them as two separate matrices to start with. So again, where we're going to start with getting the inverse, we have to do each column of the inverse independently. So we will start with the lower matrix C, and we want to solve for a column D. So since we're solving for the first column of column D, only the first row will have a 1 in it, all others will have a 0. We will solve for this with the row operation. You can see that D1 just corresponds to 1. Oh, I apologize. Corresponds to 1. D2 corresponds to 0.3. And corresponds to 0.055. Now we will back substitute the values we have found for d in this equation here. U of x is equal to d. What we're doing is we're taking the reduced row, near reduced row echelon form, multiplying it by x, and it will be equal to the d matrix we just found. Solving for all of these values, we can determine that the first column of the inverse matrix is as follows. Now again, we will have to repeat the same step for each column. Here I went ahead and did them both in a single slide so we can see the differences side by side. When we were computing for the first column, we set 1 in the first row of the solution matrix. We are solving for the second column, so the 1 is in the second row. Also, corresponding with that, 1 will be in the third row of the solution matrix in the last one. The corresponding values can be displayed here at the bottom. We can see that 0, 1, and negative 1.148 for row 2, and 0, 0, and 1 for the last column here, corresponding to the last column of the D matrix. Again, we'll follow the same strategy of back substitution. For these two methods we have found, we will again take the upper matrix times column 2 of our inverse matrix is equal to the D we just found, and we do the same here, except we take the upper matrix times our column 3 of the inverse matrix times the D we just found. Now we found x, column 2's inverse, and x for column 3's inverse vector. Now we can combine all of those simply just by putting each row in the corresponding section. This is from what we found in column 1. This here you can see is column 2, just transposed directly in there, as is here also. One of the key parts is to check here. We can also verify that this is correct by multiplying this A inverse times A, and we should get the identity matrix for that. If there's any other questions, please feel free to post them on the discussion area in Blackboard, and I will give feedback to those. Thank you.